Previously, I had mentioned that the fringe field from a battery can cause electrons to flow through an electric circuit, or any charge carrier for that matter. And I had also mentioned at that point the possibility that we could be adding some sort of resistive load into that circuit. So now I'd like to turn my attention to thinking about the resistive load. So such a device, we can call it a resistor. There are different ways you can design it, but I think the most intuitive way is to think about literally what you do in your toaster. In your toaster, if you go and take a look in the slot of your toaster, you'll see a bunch of thin wire run back and forth in a zigzag pattern. The zigzag pattern being carefully chosen to try to make the toast as uniform as possible. But the point is that you are actually running the electric current through a thin wire. And one of the things that we'll see is that the analogy between electric current flow and water flow, as I mentioned before, is an exact analogy. So with that sort of thing in mind, I've modeled here a resistor. This is a bit of normal wire over here, a bit of normal wire over here, and I'm just doing a long, thin wire here, sort of like what you would have in a toaster. Let's say, for purposes of discussion, that the conventional current is flowing to the right. Now, for all the materials that we have here, the mobile charge carriers will be electrons. So which way are the electrons going to flow? Go ahead and pause the video and get back with me. Yeah, the electrons will be flowing to the left. Remember, conventional current is the direction that positive charges would flow, and if it's negative charges flowing, it's the other way around. So if I look in the wire, I can focus on one particular electron, let's say this one here. And it'll be drifting along like so. And what's making that happen is we have within the wire, we have a fairly weak electric field. I'm just going to draw a single line just to give you an idea of how weak it is. But we have an electric field within the whole wire, even though I'm only drawing one line. So the electron, because it's negatively charged, will feel an electric force over to the left, like so. And the reason why the electron doesn't keep just picking up speed forever is that it'll keep colliding with partially shielded nuclei in the wire. And that's going to create a friction-like effect. The fancy term is phonon exchange. We don't need to go there. I'm just going to call it a fake friction. That's why I'm putting it in quotation marks. And the point is that the forces are balanced, at least in aggregate. And so our electron casually drifts its way through the circuit. And in fact, in a typical electric circuit, this isn't very fast at all. The electron will typically be moving less than a millimeter per second. The reason why we see anything happen with our electrical devices is that the electric field sets up very quickly indeed, and then the electric field just interacts with whatever electrons are there. Okay, so that's happening over there, and similarly over here we would have exactly the same kind of analysis. Our electron will be doing a nice slow drift. So this is V sub d for drift velocity. Our electron will be doing a nice slow drift against the direction of conventional current. Now, thinking back to when we talked about water flow, remember what happened when you put your thumb over a garden hose? With that thought in mind, what I'd like you to do is predict for an electron that's in our constriction here, is this electron going to be going faster, slower, or the same speed as electrons in the wire? Pause the video and get back with me. Yeah, so the electron in the wire is actually going to have to be going a heck of a lot faster. So it'll have a much higher drift velocity than you would in the wire. And the reason for this is simply you're going through a constriction. And we have to have the same number of electrons moving per second through this chunk of the wire, or this chunk of the wire, or this chunk of the wire, or else we don't have a uniform current, and that wouldn't make any sense. So if we've got this constriction here, in order to put the same number of charges through here per second, they're going to have to go faster. This is the exact same thing that happened when you put your thumb over the end of the garden hose and you saw that the water went out the constriction faster than it did if you didn't have your thumb over it. So now the question is how does the electron know to go faster? We know that it has to go faster in order to keep the number of charges moving through a second, but how does it know how to do that? What made that happen? And what we can think about here is what happened in the lead up to us establishing our steady state electric field configuration. So we've got our electric field going to the right through both our wire and our resistor here. And so if I remember that for a conductor, the electrons can just rightly be thought of as being an electron cloud. The whole electron cloud will actually shift over a little bit, like that. This is because every electron is feeling a force to the left. The whole electron cloud shifts to the left a bit. Same deal over here. The whole electron cloud will shift to the left a bit, like that. So what that means over here is we'll have a buildup of excess electrons on this surface here. Let me use a different color to mark the electrons. Yeah, there we go. Well, they have a buildup of excess electrons over here, and we'll have left behind partially shielded nuclei, so we'll have a buildup of excess positive charge over here. So this means in addition to the electric field that we had going through the wire, I now have a bunch more electric field lines that start from here and go to there. And it's just simply because initially the charges were being pulled along by this electric field, and they just literally couldn't go any further, and we created this charge distribution. But now what that's doing is within the resistor, like so, we have a much stronger electric field inside the resistor. Now, as a practical matter, unless you're dealing with lots and lots of wire, the electric field inside a wire is pretty weak. And so for any reasonable chunk along the wire, there will be a voltage drop because electric field lines run from high to low voltage. So like this chunk of the wire is at higher voltage than that chunk. But the deal is it isn't going to be by much. So usually what we do is we just say within the wire, the voltage drop along the wire is pretty much minimal. But here we totally cannot ignore this. The electric field within the resistor is much stronger. And so we'll end up saying that we have a rather non-negligible voltage difference across the resistor, like so. And that's what's going to allow this to go through faster. The electric field will be much stronger. This means we will have within the resistor, we'll have a much stronger electric force, but we'll have much more frequent collisions happening as well. So we'll also have a much stronger fake friction, like so. And again, we'll be drifting through at more or less a constant speed. There'll be a much higher speed than in the wires. Now, to characterize just how hard you have to work to get the electrons to go through the resistor, we cleverly define a quantity called the resistance. And is defined to be the voltage difference that I apply across the resistor over the current that I end up getting to flow through the resistor as a result. So in other words, this is kind of what I had, this is what I want to get, this is what I had to pay to get it. So this is effectively the price in voltage, if you will, that I have to pay per amp of current that I want to pull. Now, one of the annoying trends that we're going to see in electronics is pretty much any time we multiply or divide two units by each other, we end up creating a new derived unit. So the unit of resistance is the ohm. And it turns out that's actually the guy's name, Georg Simon Ohm. And unlike a lot of units where random letters are truncated off, you're already down to 3 to begin with. So, however, as a bit of conservation of silliness, the symbol for an ohm is a capital Greek omega. So this is 1 volt per amp. And the way you draw an omega, if we go back to the special paper that we all used in 2nd grade, start down here, you're just basically making yourself a horseshoe where you're raining the good luck down like that. Now, it turns out that as far as what reasonable values will be for typical devices, there's actually quite a range. You don't have to try very hard at all to find devices where the resistance is as low as 1/10 of an ohm or as high as 100 mega ohms. So it's a pretty good range here for what would be typical values of resistance. Okay. And this will now go ahead and introduce what I'm going to call Ohm's model. Every book out there will call it Ohm's law. I'll put law in quotation marks, and you'll see why I'm not that impressed to call it a law. So if I plot as a function of the current going through the resistor, the voltage difference across the resistor, for pretty much any resistive device, what we'll see is that it's going to end up looking like a cubic. Like so. Or at least cubic's pretty decent choice there. However, if I zoom in close enough into any particular region, like say right here, in this region here, this is nearly linear. And I do have to say nearly linear because even with not all that impressive of equipment by today's standards, for instance, just buying a multimeter at your local big box hardware store, they're good enough at this point that if you simultaneously measure the voltage across a device and the current flowing through the device, you can pretty clearly see the ohmic behavior. But it's still not a bad approximation. And for a lot of devices, you can say you can design them so that they're linear enough. So in this region here where it's nearly linear, we call this the ohmic region of the resistor. And basically the whole point is within this ohmic region, we can go ahead and say that the resistance is a constant. So then this will allow me to say that I have a direct proportionality between the applied voltage and the current flowing through. And the way I remember it is twinkle, twinkle, little star, delta V equals I times R. Now, for real-world devices, the resistance is not going to be a constant, but often you can engineer them to be constant enough, and that's good enough for most application. So just to give just a rough sense of it, let's say I just have a 10 ohm resistor. They tend to look like little sort of ceramic colored cans that have some material inside. So we'll say this is a 10 ohm resistor, and I went ahead and put a 100 volt potential difference across it, and I want to know what is the current flowing through it. Well, I can start with twinkle twinkle little star, delta V equals I times R, solve for the current, and get that this will be 100 volts over 10 ohms. And remember that an ohm is a volt per amp, like so. So this will give me 1 over 1 over amps is amps, and indeed this would be a 10 amp resistor. And this actually works out pretty well. For these kind of resistors that you purchase, there's a whole way of marking what the values are using color codes. And the last band of color that you have on these things indicates the manufacturer tolerance. If there is no band, then they're saying it's ohmic plus or minus 20%. Otherwise, other colors of bands indicate plus or minus 10%, plus or minus 5%, plus or minus 2%. So for a lot of practical design choices, that's ohmic enough, and they're just saying within the operating range, the true resistance will drift only a couple of percent over whatever the marked value is. And that's usually fine because since these things get hot because of all the collisions of the electrons with the partially shielded nuclei in here, those nuclei get agitated, which makes them hot. In fact, that's also the reason for this cubic behavior that you see here. The more current I have going through, the more frequent the collisions, the hotter the material gets. That's going to make the atoms vibrate more aggressively that are being collided with. And so it's just like, a guard in basketball who's busy jumping back and forth side to side to make it harder for a player to get past them. It's the same kind of deal with the atom. The atom's vibrating more violently side to side. It's harder for electrons to get by. And that's why you tend to see the nonlinear behavior. It's just it heats up, and that's what happens. So in the region where it doesn't heat up too much, we can get away with saying that this is close enough to a straight line for whatever we're doing. But it is a practical matter. As the resistor sits in the device, its value is going to change because of the thermal stresses. So engineers who design things have to expect the value to drift. So then that's why it's good enough to just go ahead and treat it like it's a constant in most application. All right. One of the things, so that does get us to concerns about power as well. But resistors will have power ratings. And we can also talk about the power being delivered by a battery. So we'll start with the power being delivered by an EMF source. So a battery, a generator, something like that. So for the power being delivered by an EMF source, that's going to be the change in the electric potential energy of the charges passing through the EMF source, so say the battery, over time, because power is just the rate at which energy changes. Now, how is this going to work out? Well, the EMF source has a constant voltage, the EMF, and in that amount of time, delta T, you move some amount of charge, delta Q, like so. Well, we can look at that and say, oh, hey, delta Q over delta T, that's the current. And so we can say that the power delivered by an EMF source will be equal to the current flowing through it times the battery EMF. You can kind of remember it as easy as pi, P-I-E. Now, on the other side, being dissipated by a resistive device, like so. That's going to be the same logic. It's going to be the time rate of change of the electric potential energy of the electrons flowing through. So that will be the voltage difference that will have gone across, will be the voltage across the resistor, like so. And we will have moved some amount of charge, delta Q, in that time, delta T. So again, same logic, delta Q over delta T times our voltage difference. And so this will give us that the power dissipated by a resistor will be the product of the current through the resistor times the voltage across the resistor. And this is always true, regardless of whether the device is ohmic or not. However, if the device is ohmic, we have two more expressions we can use. So if the device is ohmic, by twinkle twinkle little star, delta V equals I times R, we can say, well, delta V is I times R. So we can also say that it's equal to I squared R. That's one way we can do it. Or we can also rearrange it to get delta V squared, over R. And these are, I mean, honestly, I probably use these about all equally often. This one, this one, this one. Because most of the time we'll be worried about ohmic devices. If for some reason you're concerned that the device isn't ohmic, this one is always true. All right, so as an example of that, we can think about a hairdryer. So if you've ever looked at a hairdryer, you'll notice that there's usually a switch that will say 120, 240 on it somewhere. And this is because hairdryers can be used anywhere in the world. But when they rate the hairdryer, they always say that's like, say, a 1500 watt hairdryer, for instance. Now, what do they mean by that? What they're saying is if this is being sold in the US, they're expecting to be plugged into an American wall. So they're saying that this is really advertising the resistance. So they're saying that the resistance is such that the power dissipated will be 1500 watts if plugged into a 120 volt outlet, which is the standard in North America. However, in most of Europe, it's a 240 volt outlet, thus the little switch. So you have to remember, so it's not enough to just get the little adapters that change the shape of the plug between American plugs and European plugs. You also have to remember to throw the little switch. Now, probably almost everybody probably knows somebody who took a hairdryer over from the United States to Europe and forgot to throw that little switch, and then they promptly complained about having melted their hairdryer. So let's go ahead and figure out what would happen here. So what I want to know is what would be the power dissipated if I forget to throw the switch and I plug it into into an outlet in the European Union, which will typically be 240 volts. So we can do this as a scaling problem. We can say that the power dissipated in the European Union over the power dissipated in the US, well, the resistance will be the same in both cases if I forget to throw the switch. The whole point of throwing the switch is you actually change the resistance of the hairdryer. But if you forget to throw the switch, then the resistance is the same. So the power dissipated in the European Union will be the voltage in the European Union squared over the resistance of the hairdryer. And in the US, it would have been the voltage in the US squared over the resistance of the hairdryer. The resistance of the hairdryer only depends on the materials used to make the heater element in it. So the R's just cancel. I can rework the algebra a little bit to get that the power dissipated, if I forget to throw the switch in the European Union, will be the power dissipated in the US times the ratio of the voltages squared. So this will be 1500 watts times 240 volts over 120 volts squared. Well, this is 2 squared is 4. Turns out if you forget to throw that switch, your 1500 watt hairdryer promptly became a 6000 watt hairdryer, and that's why the thing melted down. All right, so in the next video, we'll talk a bit about materials considerations for designing resistors, and we'll introduce Kirchhoff's node law. Catch you over there.